Section 3.8 is Newton's method. It's basically a complicated way of finding zeros that you can use instead of your calculator, instead of your graphing calculator, using calculus. But it gets at some important concepts that we have learned so far in this class, and it's kind of an important one to know. It's kind of a fun one to know, actually. It uses what we call iterations. So first of all, let's understand the concept of Newton's method. Consider a function that's continuous and differentiable over the interval from a to b. You've seen that language before. If the function at a and the function at b differ in sign, then that means that the graph must have crossed through the x-axis at some point. Does that make sense? Yeah? It's totally up to you. No. This is the easier wording. I'm explaining it better than the book ever could, I think. So, if the function is continuous and differentiable, and the sign at the endpoints of the function is different, then there must be a zero somewhere over the interval, okay? That's just kind of logic happening there. So, just to picture that, if we had this is a right here, and let's make this over here b, then the function at a is sitting right here, it's positive, some value. The function at b is sitting right here, it's negative, some value. So therefore this top part right here is true. The intermediate value theorem then tells me that I must have some sort of zero over the function. Remember the intermediate value theorem? Okay. So Newton's method gets at this idea. Because of the fact that we have this situation going on here, maybe I don't have a graph sitting in front of me. It's easier to picture Newton's method with a graph, but you might not have a graph sitting in front of you. So the idea of Newton's method is that if I choose a point on the function in the interval that is close to the zero, so maybe I pick that point right there, just on a whim. I mean, I have no idea. Maybe I don't have this graph at all. So I just figure that there's a zero somewhere in the interval. I kind of estimate that maybe it's around 1, so I pick something around 1. Now if I find the equation for the tangent line through that point, then what happens is, for this particular point that I picked, I get a tangent line that comes down and crosses the x-axis very close to the actual zero. You see that? Okay. It's not a great line, but you get the idea. So, now take that resulting x value that you get, treat it like an x coordinate, plug it into your original function, and you'll get an ordered pair that's right there. Now I can take the same thing that I did before and apply it to this point. Not exactly at the zero, but I know I'm closer. So now I can make a new tangent line that goes through that ordered pair. It will cross the x-axis somewhere very close to the actual zero. Wherever that line crosses the x-axis gives me a new x-coordinate that I can then plug into my function to get a new ordered pair. Then I can do that again, a new tangent line that goes through the x-axis, and now you can see that I'm getting very close to that actual zero. Just repeat that process. Plug that x-coordinate for the x-intercept in from that tangent line that we just got, get a new ordered pair, create your new tangent line, and we can just get closer and closer and closer until eventually we're so close that we can actually say that we've approximated that zero. So the process here is pick an x value. Find the tangent line. Find where it crosses the x-axis. Plug that number in. Get a new ordered pair. Find the tangent line. Find where it crosses the x-axis. And then repeat over and over until you get to the end here. Okay, that's Newton's method. We're just approximating zeros, basically using what we've learned so far. Repeat the process until the desired level of accuracy is reached. A lot of times in these problems they'll tell you, I want a certain degree of accuracy. So that's what you'll have to do. So here is Newton's method sort of developed for you. Use point-slope form to set up your formula for Newton's method. We know point-slope form is y minus y1 equals m times x minus x1. Then, keep in mind that the slope of the tangent line, so this right here, is the same as the derivative of our function evaluated at your point that you picked, okay? So this m is actually going to turn into f prime at x1, that first x value that we picked. So right away we turn that m into f prime at x1. Now because our ordered pair is going to be written a little bit differently, we have f at x1 here, x1 comma f at x1. So let me just take a look at my graph again real quick. It's the same exact graph we were looking at. I happen to pick this point right here, which gives me an x value and a function evaluated at that x value for that ordered pair. So that's where these two things are coming from, x1 and f of x1. The slope of this tangent line that I've created is going to be, take the derivative of whatever function it is, so f prime at x1, and that's what I've written down right here. The ordered pair that we have is x1 comma f of x1, so that's why this x1 right here is still x1. This y1 right here turns into f at x1. So now if I solve this equation for y, I need to add whatever this is to both sides. So I get y equals this whole thing, f prime of x1 times x minus x1, but then plus the f of x1. Now remember that I'm trying to find the 0 here. So now I have my tangent line sitting here. This is the equation for my tangent line, incidentally, sitting right here. If I want to find where that tangent line crosses the x-axis, then I set y equal to 0, because the y-coordinate when we have an x-intercept is 0. So I turn this into 0, and then I solve for x. Now I don't show the work here. I can show you the work if we need to, but basically all I'm doing is I'm taking this equation right here, and I'm solving for x once I make y 0. Once I've solved for x, then I wind up with x1 minus f at x1 divided by f prime at x1. So what that says is my x-intercept for my tangent line sitting right here, whatever it is going to be just the x-coordinate that I picked minus the function evaluated at that x-coordinate divided by the derivative of the function evaluated at that x-coordinate. And because of the fact that I used algebra this whole time, this is always going to be true no matter what x-coordinate I pick. It gives me an estimate for a 0 using this method, and this is Newton's method right here. This x is your second approximation of the 0 for your function. Your first one was the one that you picked. So I could actually call this x2 right here equals x1 minus f at x1 divided by f prime at x1. So this approximation that we have right here is now x sub 2. So just keep in mind that we picked this x value right here first, which gave us that ordered pair. Now we're on the tangent line, and we're only going to be on the tangent line. So on my tangent line, by setting this equal to 0 right here, I'm finding where my tangent line crosses the x-axis. It's right there. Now when I plug in x2 into my function, I get this ordered pair sitting right here. So this would be like x2 comma f at x2. Then I'm creating my new tangent line that cuts across the x-axis right there. That's going to wind up being x3. And then I'd have x3 comma f at x3. And then I'd have a new tangent line that cuts across the x-axis right there, and that would be x4 comma f at x4 when I plug that in here. And then I just keep going. That gives me x5 and x6 and x7, and I can keep going. I can go as many times as I want, but we'll get to a point very quickly where there's no need to continue. So here's your summary. Your first estimate of the 0 was x1. That's the one you pick. Then you find your second estimate using x2 equals x1 minus f at x1 divided by f prime at x1. Then you use that result to find your third estimate. It would be x3 equals, and now you're using your x2 that you just found, x2 minus f at x2 divided by f prime at x2. And you can keep going forever if you wanted to. Repeated application of this process is called an iteration. You've done iterations before, actually. Any sequential next x value would be x at n plus 1, x sub n plus 1. And you're going to find that by taking x sub n minus f at x sub n divided by f prime at x sub n. That's Newton's method, this guy right here. Most of the time you're going to be asked to approximate a zero-sum desired level of accuracy. A lot of the times it'll be 0.0001. I think that's what I have here. Do I have that on here? No. I probably will, though. Usually the desired level of accuracy is sequential approximations of x differing by less than 0.0001. And that's pretty accurate. I mean, that's accurate to 1/10,000th of a place, basically. That's really accurate. And you're going to see that this actually happens very, very quickly. Usually within 2 or 3 approximations you'll be done, because your answers will differ by less than that fast. So when the absolute value of x sub n minus f sub n minus 1 is within that desired level of accuracy that I just wrote here, then you're done. F at x sub n plus 1 is the final approximation. And if you're not there yet, if you look at your 2 approximations, like x sub 2 and x sub 3, and they don't differ by less than that, then you just do one more, and then double check it again. And if that doesn't work, then do one more. It doesn't take that long. Okay, so let's just start with an easier example. Calculate 3 iterations of Newton's method to approximate a 0 for f of x equals x squared minus 2. Use x sub 1 equals 1 as your initial guess. So I'm telling you just strictly 3 iterations of Newton's method. And I'm giving you x sub 1 already. So we just need to find x sub 2 and x sub 3. Once we get to x sub 3, we are done, I believe. Sorry, x sub 4. 3 iterations. So x sub 1 to 2 would be 1 iteration. 2 to 3 would be 2, and then 3 to 4 would be 3. Okay? Okay. So, and I'm telling you to use x sub 1 equals 1 as your initial guess. So here's my graph right here. X sub 1 is right here. So I am starting on my curve right there. I don't need to know that. I don't have to see the graph at all. All I have to do is know that there's a 0 somewhere in that region. And if I go with an interval from 0 to 2, I'm negative here, I'm positive here. Obviously, there's a 0 somewhere in between. So if I pick 1, that's a kind of a reasonable guess. Okay?
Are we going to have to do it, like, because it's a problem where you have to do intercept? How do you do it?
It just says find a 0, approximate a 0. There are 2 zeros here, but we only need to find one of them. Okay? So we're using x sub 1 as our initial guess. We need, first of all, to find the derivative, because remember that our Newton's method is x sub n plus 1 equals x sub n minus f at x sub n over f prime at x sub n. So we definitely have to have the derivative. We have the original function. So we're just going to have to do some math, hopefully, in our heads to help us get through this. F prime at x equals what? 2x. Okay, now x1 equals what? What's x sub 1? It's 1. We're told to use x sub x1. X sub 1 equals 1. Okay, so then x sub 2 equals x sub n, which is 1, minus f at x sub n. So I take 1 and I plug it in. 1 squared is 1, minus 2 is negative 1, divided by f prime at x sub n. So I take 1 and I plug it in over here. 2 times 1 is 2. So this gives me 1 minus negative 1/2. Well, that's the same as 1 plus 1/2, which is 3/2. I want to stick with the fractions here for as long as I can. for no particular reason at all. So that's x sub 2 right there. That's our first iteration. We can see that 3/2 is pretty close to that 0, but it's definitely not exactly. So we'll do x sub 3 equals, what will I write? 3/2 minus, now the numerator. So 9/4 minus 2. 9/4 is 1/4? Just positive 1/4 or negative 1/4? Positive 1/4 divided by 6/2 reduces down to 3. So we have 3/2 minus 1/4 divided by 3, which is 3/4 divided by 3 is 1/12. So we have 3/2 minus 1/12. Common denominator, so 3/2 turns into 12ths. That would be 18/12 minus 1/12 is 17, so 17/12. 2 iterations done. Now we need the last iteration, x sub 4 equals 17/12. Okay? (17 squared). Something that ends in 9 maybe? Maybe it ends in 3. 289. So 289, what? (289 1/44) minus 2. Well, think about it. There you go, 1 1/44. You just did that on a calculator, right?
Yeah, and then I realized what it was.
Yeah, 1/44 would be the common denominator for this 2 right here. So you just double that and you get 288 1/44. 289 minus 288 is 1 1/44. All of that is divided by 2 times 17/12, 17/6. Yeah? Okay. All right, now we got to figure that out. So we have 17/12 minus 144 divided by 17/6. I'm just going to write that down. We have 17/12 minus what? 144 times 17. 6 over 144 times 17 reduces down to 1 over 408. So we have 17/12 minus 1 over 408. We're getting there. Common denominator. Does 12 go into 408? 34 times. So it does. So we have 34 times 17 minus 1. 577 over 408. Now, wouldn't you love it if I asked you to do one more iteration using those fractions? No, definitely not. So we're going to stop there. Now, tell me, what is the decimal approximation of 577 over 408? 1.4. Give me more decimal places. 41422. Okay. Sounds nice. I don't know. So let's think about this now. Let's actually take this equation right here and solve and find the actual zeros.
Oh, that's the x value
we set y equal to 0, and we get x squared minus 2 equals 0, right? Add 2 to both sides, square root both sides, and you get plus or minus the square root of 2. So what is the square root of 2?
Like 1.4.
Let's get the actual to the same degree of 2, 1. So in just 3 iterations here, we came up with almost the, I mean, it's getting close, right? Just in 3 approximations. So it is a very good method for approximating zeros. And you got to remember that this was developed in a time when we didn't have graphing calculators. We didn't have software programs or the Twitters, right? So this is a very good method, and it happens very quickly. Typically, you won't go more than 4 iterations if you have to go more than 2 at all. Next one, use Newton's method to approximate the zeros of that polynomial. Continue until successive approximations differ by less than 0.0001. And as we just seen, it's not going to take very long to get to that degree of accuracy. Okay? So, based on the graph that I have here, and this is how you do this, by the way, you just graph that thing or get an idea of where that thing crosses the x-axis approximately, and then pick a number that's close to that 0 to get started. Sure, because you're going to use your calculator anyway to come up with these approximations. Yeah. And then obviously the calculator could calculate that for you, but you want to, if it asks you specifically to go through that process, then you want to go through that process. Right. So, what should we do? Take a look at the graph first. -1, you think? So we need an x sub 1. We need a place to start, somewhere that's close, that gives me an easy number to begin with. It would be that -1. Okay, so now the derivative, f prime, of x equals? Yeah. All right, now what? Okay, actually before we do that, yes, you're right. But think about this polynomial. Is there any way that you guys are going to be able to factor that somehow and get it down to where you could split it apart using the zero product property? Do we have can we use the quadratic formula here? No. So there's really no way for you to get this thing down to where you could calculate that 0 without doing a bunch of guessing and checking for forever. Okay? Yeah, it'd be terrible. So that's why Newton's method is great. So I'm going to write x sub 2 equals
-1 minus.
Okay, so think about that. No. Wait, yes? What'd you get? Is it 1? 1? Okay. So we have -1 minus 1 over what? 3? Okay, I'll buy that. Simplify that down, what do we get? -4/3. Okay. Now, did our successive differences differ by less than 0.001? No. So we got to keep going. Now what? All right, some stuff. You can do this.
If only we had a device that
You can do this.
Newton didn't have it, we don't need it.
That's right, we don't need it right now.
All right.
Your brains are going to grow slightly here.
4 times 4 is 16 times 4 is 64.
64 over
3 times 3 is 9 times
27. Now, is it a positive 64/27 or a negative 64/27? A negative 64/27. But then it's times 2. Times positive 2. So we have negative, I'm just going to write it over here, negative 128 27ths. Then what? It will be plus.
This is going to be a positive. We can split it up in
16 ninths. Plus 4/3. Okay.
Yay, common denominator.
Common denominator is 27.
We can leave the first one.
So you want to write it all down? We'll write it all down. Plus 48 27ths plus 36 27ths plus 27 27ths. Now I know it's Monday morning and it's right after Thanksgiving, so we probably could have done this in our heads, but I'm feeling pretty sluggish. So add all that together. I'm going to add these two things together here, and I get negative 17. Wow, your brain's working pretty good.
Nick didn't have a calculator. He don't need one either.
So it's negative 17 over what? 27. Now divided by? It's not. Sixteen ninths times 6. Well, 16 ninths times 6 would reduce down to, it's basically 96 what? 16 ninths. Think about it. 16 ninths times 6. This is going to reduce to 2/3. So it's really 2 times 16, which is 32 thirds. Right? Okay. 32 thirds plus so minus 8 thirds. Where are we at now? 32 thirds minus 8 thirds would be 24 thirds, which reduces down, doesn't it?
8 minus 1 is 7. Yay!
That wasn't so bad.
So that changes to
Now, we got to simplify that down.
189.
189.
Negative 17 over 189.
How did he do this?
So we have, okay, we have a denominator here of 189 now. Negative 17 over 189, but it's negative negative, so it's actually positive 17 over 189. So we have negative 4/3 plus 17 over 189. What do we get? I'll do the hard part. It's negative.
Did the stars just align or something when he did this?
Like, we're using this to calculate when the stars align.
This is what people did for entertainment back in the day. They didn't have to update Facebook every 20 minutes. They had lots of spare time.
They have to take pictures of their food.
235 over 189. What is the decimal approximation there?
Wait.
My guess is like
1.24. Remember, we need this degree of accuracy. 339. What's the decimal here?
Negative 1.33333.
All right, are we differing by less than 0.0001? No, so that means we have to do one more, maybe.
plug it into the calculator.
Plug it into the calculator?
Yeah, Newton had a lot of free time. We do not.
Okay, I'll give you that. So here's how you do this using a calculator, which is way, way better than doing this by hand. What was our x1? No,
Negative 1 is negative 1.
it was -1. So in my calculator, I'm entering -1 in. Type in -1 and press enter.
Plus 2 is
Just do what I say. It's my planet. Now I'm going to show you something that you probably have never used before on these calculators. Next to or down by the negative sign, above the negative sign, you see that ANS right there? It stands for answer. So you probably knew that already, but you didn't know that you could use that idea to make iterations happen on your calculator, which is what we're doing. So I'm going to teach you how to do an iteration on your calculator. Because we're using the same equation over and over and over, and we're using the answer from the previous in the next, what we're going to do is type in exactly our Newton's formula, but everywhere we see x, we're going to use answer. That way, when I press enter, it will store that, and then I can press enter again, and it will take the answer from the previous and insert it into what I just entered in and give me my newest answer. So to do that, we need x1, which was -1, but I'm not typing -1 in, I'm typing answer. Then subtract. Now I'm going to create a fraction here template. You can control above the one that, above the division bar. You see the little box over a box. In the top, I'm going to type in my original equation. My original equation was 2, but it's not going to be x, it's going to be answer to the third. Then plus answer squared. Then minus answer. Then plus 1. Then the denominator is going to be the same thing, but with the derivative function instead. So it'll be 6 answer squared minus 1. Once you have that look, double check it to make sure that everything is correct. Then what we have here, before we press enter, is we have x1 minus 2 times x1 cubed plus x1 squared minus x1 plus 1 divided by 6x1 squared plus 2x1 minus 1. That's basically what we were doing, except we were plugging all those numbers in. Now because we have this set up, when we press enter, it's going to give us an answer. But if we press enter again, it will repeat that same entry that we just had using the answer that it last got, which in this case is -1, but in the next case it will be -4/3. So press enter. Actually, I'm pressing Control Enter to give me the decimal approximation because that's what I want, and it gives me the -4/3. Press enter again, and it gives me my -1.24339, which we calculated. Press enter one more time. 1.23386. We're still not there. Press enter one more time. -1.23375. We need to differ by less than 0.0001 though. And right now we are 0.0001, but it's not quite. So one more. I mean, it's not that hard to press enter one more time, and we get the exact same result based on what we see here. So therefore, my answer would be -1.23375. And that was x4. Control enter for the decimal. Always control enter for the decimal on this one. Once you press it once, you don't have to press it every time, because once it goes to decimal, it stays there. But that's the answer, okay? x4 gave me that. X sub 5 gave me that exact same thing. So therefore, that's our answer. A couple of cautionary things about Newton's method. Each successive approximation seems to approach a limit. When that happens, the sequence is said to converge. If you are approaching a limit that does not change in the end, then the sequence converges. If the sequence does not converge, then it diverges. It goes away from some like horizontal asymptote type thing. There are cases in which Newton's method does fail. When would this method potentially fail? Looking at that equation. if this is equal to 0, when you have a critical number, if you were to accidentally pick a critical number or accidentally pick a number that wound up giving you a critical number, then it's going to fail. So yeah, if my graph does this, if I'm just using that same kind of curve that I was using before, if I accidentally pick that exact number right there, the derivative here is 0. I'm never going to get down to that 0 down there, okay? What if I happen to pick, if the critical number is the 0, I don't think that would fail. So if I happen to pick a number here that gave me a tangent line that happened to come down and hit that critical number right there, so that I wind up with 0 here now, then that would also fail. Okay? So all you have to do is just make sure that you're careful about your x sub 1 choice. When you take the first derivative, you'll be able to plug in your first x1 and make sure that you don't get 0 for your derivative to avoid that mistake. Okay? The other place that Newton's method fails is if the graph happens to go vertical at the point where the graph crosses the x-axis. So in this case right here, if the graph goes vertical, you're not going to be able to use Newton's method because you can't take the derivative at that point. Okay? So if we use x1 equals 0.01, like maybe right here, then here we are at my function. I draw a tangent line. Tangent line crosses here. Go back down to my function, draw a tangent line. Tangent line crosses here. We're getting farther and farther away, which is known as diverging. We're diverging away from the 0. Yeah, divergent, that's right. Okay, so in that case, Newton's method would also fail. Okay, we have one last problem to try here. Use Newton's method to find x4. Meaning the fourth approximation of the positive root of this polynomial right here. You can choose your own x1 close to the root. Go. So I want to see this. x1 equals your choice. Then x2 equals whatever you found on your calculator. Then x3 equals whatever you found on your calculator. And then x4 equals whatever you found on your calculator. I'm looking for x4. So once you graph it, you see that there really is only one 0 that appears to cross somewhere near 2. And once you enter that into your calculator, press enter, then you can enter in the iteration formula. And once you do that and press enter, you got 2.33333. Or if you were like me and forgot to press control enter, you got 7/3. Then I remembered to press control enter, so I pressed control enter this time and I got 0.56. And then x4, which is the one I'm looking for. Okay. Now you could continue from there. Did everybody pick 2 as their original? Had you not picked 2, had you picked 1, would you have gotten the same x4? It's an interesting question. Or if you had picked 3, would you have gotten the same x4? The answer is maybe not exactly in these last 2 here, but you definitely would have been very close there.